Assalamualaikum. Today we are going to start section 5.2 from chapter number 5, and this is about segment notation and limits of finite sums. So summary of this section is as follows. First of all, we'll find a convenient notation for sums with large number of terms, and then with the help of this notation we'll look at what happens to finite sum approximation as the number of terms approaches infinity. So segment notation enables us to write a sum with many terms in a compact form. For example, if we have this sum a1 plus a2 plus a3 up till an, how can we write this sum in one term in segment notation? See, this is how we can write this sum in this form, sigma in the sigma notation. So this sigma notation is called sigma because of this sigma. This is a summation symbol, which is Greek letter sigma, and this is the starting point of index. So index k starts at k is equal to 1, and k is the index, and the index k ends at k is equal to 1, and ak is the kth term of the sum, or ak is the formula for the kth term for the given sum. Now we can write the sum of squares of the numbers 1 through 11 as 1 square plus 2 square plus 3 square and so on up to 11 square. Now the question here is, how can we write it in segment notation? So see, first term is 1 square, second term is 2 square. So we have to find the formula for kth term. Third term is 3 square. Fourth term is 4 square, and so on. Kth term is k square. So we can write it as sigma k square, where k varies from 1 to 11, right? So the starting point of the index is 1, and the ending point of the index is 11. Again, the sum of fi for integers I from 1 to 100 can be written as f1 plus f2 plus f3 and so on up till f100, the sum of first 20 terms. So how can we write it in the sigma notation? Again, we have to find the kth term of this sum. So first term is f1, second term is f2, third term is f3. So what will be the kth term? It's quite obvious. Kth term will be fk, or index can be I, index can be k, index can be r, or any letter can be used as the index. But in this case, the sum fi for integer I. So in this case, we have to find the ith term, right? So which is fi. So let's see how does it look like. So there is the sigma notation for this sum. Sigma I varies from 1 to 100. Index here is I, and ith term is fi. In the initial point or the point where index starts is 1, and where it ends at 100. So here is the sum of 4 terms, and we have 1 over 2 plus 1 over 4 plus 1 over 16 plus 1 over plus 1 over 8 plus 1 over 16. Now this is not quite obvious actually to find the kth term for this. So what we need to do, let me write. Our first term is 1 over 2. So first term is 1 over 2 plus second term is 1 over 4, and it can be written as 2 square, plus third term is 1 over 8, which can be written as 2 cube, plus fourth term is 1 over 2 to the power 4. So what is the kth term? Kth term will be 1 over 2 to the power k. So the sum for these 4 terms can be written in sigma notation as sigma k varies from 1 to 4, because we have 4 terms, we have to add 4 terms, and kth term is 1 over 2 to the power k. Okay, let's try one more question. So this is the question, and there is a twist. There is alternate sign change. First term is positive, second term is negative, third term is positive, and then negative, and then positive. So what to do? Okay, first term is 1 over 1 minus, and the sign is positive. Sign of first term is positive, sign of second term is negative. Okay, and 1 over 2. So third term with positive sign 1 over 3, negative sign 1 over 4. This is fourth term, plus 1 over 5. So kth term will be 1 over k, but what will be the sign of the kth term? So this is the question. So this is the first term. Okay, that is, this is a1, and its sign is positive. So sign is minus 1 to the power 1 plus 1. Okay, so this is the second term, a2, and its sign is negative. So what we need to do, 2 plus 1. Okay, so we have to add 1 in the number of term, minus 1 to the power number of term plus 1 will give us the sign of the term, kth term. So how can we write it in sigma notation? So here we go. K varies from 1 to 5 because we're adding 5 terms. Minus 1 to the power k plus 1, 1 over k. Kth term is 1 over k, ignoring the sign. But in order to determine the sign, we'll have to write minus 1 k to the power k plus 1 times 1 over k. So this is the sigma notation for this sum. Okay, here I have a few more examples, and this is example number 1 in your book. The sum in sigma notation is given in the first column. So sigma k varies from 1 to 5 is 1, and it can be written as an expanded form. Variable here is k, so this index will be applied on k. So 1 plus 2 plus 3 plus 4 plus 5, and this is the value of the sum. Similarly, this can be written as again variation will be applied on k. So minus 1 to the power 1 into 1 for k is equal to 1, plus for k is equal to 2 minus 1 square into 2, and for k is equal to 3 minus 1 cube into 3, and we have minus 2 answer. And this is the sum of two terms. K varies from 1 to 2, that is, it will start from 1 and end at 2, so we have only two terms. K over k plus 1. For k is equal to 1, it will become 1 over 1 plus 1. For k is equal to 2, it will be 2 over 2 plus 1. So the sum is 7 over 6. And in this term, you can see k, initial value of k is 4, and terminal value of k is 5. So it starts at 4, ends at 5. So it actually tells us that it's not necessary for k to start from 1 always, right? So this is the sum, and this is the term for k is equal to 4, and this is the term for k is equal to 5, and this is the value of the sum, 139 over 12. So there is another example, express sum in sigma notation. So in previous example, what we did, sigma notation was given, and we expressed it is in sum form, and now we have a sum form, and we have to convert it into a sigma notation. That is, we have to find the kth term. Now we can start k from 0, we can start k from 1, we can start k from any integer. So there are different values of k, starting values of k are given, and of course for every starting value of k, we will have a different formula. Formula will not remain same. The purpose is to get all these terms using this sigma notation. Okay, so let's see. If we have k is equal, if we start with k is equal to 0, then what will be the kth term for this sum? If we start with k is equal to 0, now keep it in mind that the kth term will start with 2k, because 2k is an even integer, right? When k is an integer. Whenever k is an integer, 2k is always even. Okay, we'll start with 2k and then we'll add some odd number. Because this is sum of odd numbers. So in order to make sure that the number is odd, we have to add an even number and an odd number, right? So we'll start with 2k and we'll add appropriate odd number in order to uh, uh, find the kth term for the sum. So if we start with k, so 2k, for 2k becomes 0. So what is required to make it 1? We'll have to add 1. And when k is equal to 1, we have to plus 1, 3. And when k is equal to 3, we'll have, k is equal to, yes, when we have k is equal to 2, 0, 1, 2, k is equal to 2, then we'll have 5. Okay, so these are consecutive odd numbers, that is why this is possible for us to add 1. Now, for k is equal to 1, if we start with k is equal to 1, as I told you that 2k is a must, then we will add appropriate odd number to make it 1. So k is equal to 1. If k is equal to 1, 2k is equal to 2. So what we need to add to make it 1, we'll have to add negative 1. Okay, so let's see if it works for every value. For k is equal to 2, 4 minus 1 is 3, and so on. Similarly, if we start with k is equal to 2, again, when k is equal to 2, 2k becomes 4, and what should we add to make it 1? We have to subtract 3 from 4 to make it 1, right? So, and for k is equal to 3, we have 6 minus 3, which is 3, and so on. So that is how we can start from different values. This is not necessary for us to start with 0 or 1 always. So this is the algebra rules for finite sums. That is, we can add sums, we can subtract sums, we can constant multiples, and the last rule seems a bit weird, but we'll discuss it later. So first of all, sum rule. If we have the kth term like this, ak plus bk, and then we can split the sum, sigma ak plus sigma bk. Similarly, the difference can be written in this form. This is called difference rule. Constants multiple constants comes out of the sigma notation because it does not depend upon k, which varies. So it can be any number c. And what about the last one? Sigma k varies from 1 to n of c. C is any constant. So see, how can it be n into c? So sigma k varies from 1 to n c. C is any constant. Using this rule, we can have c outside. Sigma k varies from 1 to n. And what is left inside? 1. Okay. So it means we have to add 1 n times, right? So this is equal to c. 1 plus 1 plus 1. How many times? N times. So n times adding 1 yields n. So this is equal to c n. That is why this is equal to n into c. Okay. Next, example number 3. This is actually the example how to use these rules. So sigma k varies from 1 to n, 3k minus k square can be written as 3 sigma k is equal to 1 to n k. Now the constant multiple rule is also used and the difference rule is used, right? Similarly, in this case, constant multiple rule is used because negative 1, we took it outside the sum. and sum rule is used in this case, and this is the constant value rule because 1 over n is constant with respect to k. So 1 over n, so we can elaborate it like this, that it can be written as 1 over n sigma k varies from 1 to n 1, and this sigma 1 is n, so 1 over n is 1. Okay. Okay, there are very important results to learn in order to use these sums. So if we add first n positive integers, that is actually sigma k varies from 1 to n is in fact 1 plus 2 plus 3 up till n. Okay, so we just added first n positive integers and we should have n into n plus 1 divided by 2. So this is the formula. And similarly sigma k square, that is first n squares. This is first n numbers, this is first n squares. So n into n plus 1 into 2 n plus 1 divided by 6. And these are very important formulas to use in further applications. The first n cubes, similarly sigma k cube is n into n plus 1 over 2 whole square. So I think it's all these are easy to remember, and I'm going to prove this for you. Rest you can prove yourself. So let's prove this. So first we have to prove this. Sigma k, k varies from 1 to n is equal to n into n plus 1 divided by 2. So let's start the proof. So first of all, left hand side of the equation is considered, and as I told you, it can be written as 1 plus 2 plus so on n. So this is written in forward order, that is the lowest term first and then the greater one, then the greater one, and the highest term is written at the end. And this is the backward order, that is highest term is written as the first term, and then the second highest, and so on, n minus 1 and minus 2, and this is the decreasing order and this is the increasing order. This is the forward expression, this is the backward expression. Now you can see that, you can observe that the sum of first term of forward expression and the first term of the backward expression is n plus 1. Similarly, the sum of the second term of the forward expression and the second term of backward expression is also n plus 1, and so on. This is all. This is sum of these two is also 1, and sum of the last two is also 1, n plus 1. So what does this mean? This is n plus 1. Okay, this is n plus 1. This sum is also n plus 1. So on, this sum is also n plus 1. What we are going to do, we now add all these sums. We are going to add n plus 1 n times. These are n terms. So we are going to add n terms, n plus 1 n times. Okay. Now this actually we are required the value of this sum. Okay, this value of this sum is required, right? And we are adding this sum 2 times, and we have n into n plus 1. So what will be the value of this sum if we add it 1 times? It will be the half of this. So this is how this formula is proved. Okay, so this implies this is equal to n into n plus 1 divided by 2. So similarly you can prove the rest two formulas as well. So here's an example. Find the limiting value of lower sum approximation to the area of the region below the graph y is equal to 1 minus x square and above the interval on x-axis using equal width rectangles whose widths approach 0 and whose number approaches infinity. So we have to find the lower sum approximation of this region. Okay, and you have already done this region in the section 5.1 as well, but In that case, in that section, we used actually 2 rectangles and 4 rectangles only, and then we saw the results for 16 rectangles as well. But in this case, we have to uh, approximate the lower sum as number of the rectangles approaching infinity. So let's see how to do it. As you know that if uh, there are n subintervals, then what is the length of one interval if we have n subintervals? Okay, if we have n subintervals, interval here is 0, 1. Okay, interval here is 0, 1. So if we have n subintervals, what will be the length of the interval? As I told you, b minus a over n. So b here is 1, a here is 0, so this is the delta x, 1 minus 0 over n. Now the subintervals will be 0, 1 over n, similarly 1 over n, 2 over n, then 2 over n, 3 over n, and this is how these intervals are written. So first interval starts from 0, ends at 1 over n. Next interval starts from 1 over n to n. Since this function is decreasing function, so the lower sum is actually the right sum. Okay, so the lower sum is right sum. So we'll use the value of the function as height of the rectangle at the right end of the interval. So the sum becomes lower sum becomes then f of 1 over n multiplied by 1 over n, which is the width of the rectangle, and f of 1 over n is the value of the minimum value of the function in the interval. Okay, so as I told you again and again that the function is decreasing, so minimum value lies at the right end of the interval. So right end of this interval is 2 over n. So f of 2 over n multiplied by the width of the rectangle, and so on. F of n of last interval, f of n over n multiplied by 1 over n. And this is the sigma notation of this sum f of k over n multiplied by 1 over n. So let's have a look at it again. F of 1 over n, f of 2n. When we have first term, f of 1 over n. In second term, f of 2 over n. 1 over n is common in every term. So kth term consists of f of k over n. So that is why this is written sigma f of k over n multiplied by 1 over n, k varies from 1 to n. Okay. Now what we do, we just plug in this k over n in the value of the function. F of x is 1 minus x square, so replace x by k over n. So we have sigma as it is, k varies from 1 to n. F of k over n is 1 minus k over n whole square multiplied by 1 over n. Okay, so this can be written as sigma 1 over n, just multiply 1 over n inside, 1 over n minus k square n cube, because k square we already have k square over n square inside, multiply it by 1 over n, we have k square over n cube. Now next step is done by difference rule. Okay, and the next step, in this step we used the constant value rule, n multiplied by 1 over n and minus 1 over n cube. This is the constant multiple rule because 1 over n cube is constant in this case, and sigma and k square. Now substitute the value of sigma k square, which is n into n plus 1 into 2n plus 1 divided by 6, and 1 over n cube as it is. This will make it 1, and so we have this expression which is the sum. So which is the actual lower sum. So we have obtained an expression for the lower sum that holds for any n. Okay, taking limit of this expression as n approaches to infinity, we see that the lower sum converges as the numerators of sub intervals increases and the sub intervals width approaches 0. Okay, let's see how can we find this limit. So this limit as n approaches to infinity, that is number of rectangles approaches to infinity, this sum we have to find the value of this sum. So limit n approaches to infinity, 1 minus 2n cube plus 3n square plus n divided by 6n cube. We can solve it, and you have learned this method while solving the questions for limit in calculus 1. So 1 as it is, 1 minus, now we will divide n by n cube, the numerator and denominator both. So we have 2 plus 3 over n plus 1 over n square, and when we divide the denominator by n cube, we will have 6. Okay, and limit as it is. So this is equal to limit of limit as n approaches to infinity of 1 minus 2 over 6, because this is independent of n. Now 3 over n, as n approaches to infinity, 3 over n approaches to 0. Similarly 1 over n square approaches to 0. So we are left with 2 over 6 only. Okay, so this is equal to 1 minus 2 over 6 as shown here. Okay, so this is equal to 2 over 3. Okay, next idea is Riemann sum. So we subdivide the interval AB into subintervals not necessarily of equal widths. So far we were subdividing into the intervals of equal widths. Okay, now this is not necessary to have equal widths. So we subdivide the interval AB into the subintervals not of equal widths or lengths and form sums in same way as for the finite approximations in the section 5.1. So we are, let's draw a few rectangles. Like if we have a rectangle like this and this and this. Okay, so the width of next rectangle is different, so we can draw now rectangles of different width as well. Okay, and so on, right? So there is some area, similarly there is some area, we have to find this area by using these sums. So next step to do so, we choose n minus 1 points, x1, x2, x3 up till xn minus between a and b, that is excluding a and b. So between a and b, we let's have a point, let's have n minus 1 points that are in increasing order, so that a is less than x1 is less than this increasing order, that is b is greater than a, and all these points are in increasing order. So to make the notation consistent, we assume that x0 is equal to a and xn is equal to b. So this is how it looks like, and the set of all these points x0, x1, x2, xn minus 1, xn is called partition of a, b. Now the partition P divides AB into the n closed subintervals x0, x1, x1, x2, and so on, xn minus 1, xn, as I told you earlier, that we can divide it in the intervals and they are not necessarily of equal lengths. Okay, and then we'll draw the rectangles and in order to approximate the areas. So the first of these subintervals x0, x1, this is the interval x0, x1, and the kth interval is given by this xk minus 1 xk for k an integer between 1 and n, right? So the width of the first subinterval is denoted by delta x1. So since widths are not equal, So this time we don't write delta x. Widths are assumed to be unequal. So width of the first interval is delta x1, second delta x2, and so on. The width of that kth interval is delta xk, and the last interval is delta xn. So in each subinterval we select some point. The point chosen in the kth subinterval is called ck, like this. This is the kth interval. So in first interval we chose a point c1. Now there is no rule to choose the point. There is no midpoint rule. There is no right and left sum. We are choosing any point. So c1. Similarly, c2 lies in the second interval. C3 lies in the third interval, and we will find the height of the rectangle by f of ck. So we have now what we have kth width of or length of the kth interval delta xk, and we have a point in the kth interval ck at which the height of the rectangle is fck. So the area of the kth rectangle is delta xk into fck. Okay, so this is the case. Okay, so on each interval we form the product fck into delta xk. This product is positive, negative, or 0 depending on the sign of fck. When fck is greater than 0, the product fck delta xk is the area of the rectangle with height fck and the width delta xk. When fck is less than 0, the product fck is negative number, the negative of the area of rectangle of the width delta xk, because area is always positive. So in order to find the area, we'll ignore the negative sign, or we can say that this is the negative of the area of the rectangle of width delta k, and that drops from the x-axis to the negative number fck. Okay, so finally we sum all these products to get the area, approximation for the area, which is SP. So the sum SP is called the Riemann sum, or F on the interval AB. So there are many such sums depending on the partition P we choose and the choices of the points CK in the subintervals. For instance, we could choose n subintervals all having equal widths, and in this case width will be b minus a over n to the partition AB, and then choose the point ck to be the right hand endpoint of each subinterval when forming the Riemann sum, as we did in example 5. So for this choice, what we'll have, then Sn will take this form. Now let's see how does it take this form. We have interval A and B. Okay, so since we have the subinterval n subintervals of equal length, and the length of one subinterval is b minus a over n. So delta x. So initial point is a. So what will be the this point? This is a. Since this width is delta x, so this will be a plus delta x. Okay. So what is this point? This is a plus 2 delta x. Right. So the first point is a, and then a plus delta x, then a plus 2 delta x, and so on. Kth point will be a plus k delta x. Okay. Now we have to find the right hand sum. See this. We have to find the right hand sum. Now in first interval, right hand value is a plus delta x. So what is the area of the rectangle in this case, or the product fck delta xk will be in this case f of a plus delta x into delta x. Okay, plus next in the second interval, right point of the second interval is a plus 2 delta x. So f, this product will become f a plus 2 delta x into delta x, and so on. Kth f a plus k delta x into delta x, okay, and so on. The last will be k is equal to, and last will be the point a, sorry, the point b, and b is equal to a plus n times delta x. So plus f of a plus n delta x into delta x. So all these products are added like this, okay. So now the question here is why b is equal to a plus n delta x. So we have this relation delta x is equal to b minus a over n. Delta x is equal to b minus a over n gives us b minus a is equal to n times delta x, and this implies b is equal to a plus n delta x, right? So that is why this happens. Now what is the value of delta x? Delta x, value of delta x, b minus a over n. So we just replace this delta x by b minus a over n to get this formula. Now, let me write in terms of delta x first, and then you will see. Now k varies from 1 to n. K varies from 1 to n. F of a plus k delta x into delta x. So this is the sigma notation of this sum, okay. Now replace delta x by b minus a over n, we have this Sn, right? Now this is the right sum, and if we have to write the left sum in this form, then we'll have the first point a, f of a, then f of a plus delta x, and so on, and we will end up at the point a plus n minus 1 delta x, okay, because this is the interval a plus n minus 1, b is equal to a plus n delta x, right? So this is the last interval. So left end point of this interval will be this. So if we have to write the left hand sum, then this this formula will become, let me write it here, left hand sum will become k varies from 0 to n, f of a plus k 0 to n minus 1, I'm sorry, 0 to n minus 1, okay, n minus 1, k b minus a over n into b minus a over n. So this is the left hand sum, and this is the right hand sum, okay. I hope now you understand the difference. Okay, in the cases in which all the subintervals are equivalent, that is delta x is equal to b minus a over n, we can make them thinner by simply increasing their number. We have already seen this. When a partition has subintervals of varying widths, we can ensure they are all thin by controlling the width of the widest, longest subinterval. And we define the norm of a partition P, written as norm P, to be the largest of the all subintervals width. If norm P is small number, then all of the subinterval is the partition in the partition P have the small width. So we have to just control norm of P. There is an example to find the norm of a partition. Let P be 0, 0 0.2, 0 0.6, 1, 1.5, 2 is a partition of 0, 2. Now there are 5 intervals 0, 0 0.2, 0 0.2, 0 0.6, and they are of different widths. Okay, the width of length of this interval is 0 0.2, and similarly this is 0 0.4. Its the width is again 0 0.4, so that they vary. So lengths of the subintervals vary. So delta x1 is 0.2, delta x2 is 0.4, delta x is 0.4, delta x4 is 0.5. So the largest one is 0.5. So norm of this partition is 0.5. Okay, so this is how we can find the norm of a partition. Okay, Riemann sum associated with the partition of a closed interval AB defines rectangles that approximate the region between the graph of a continuous function f and the x-axis. Partitions with norm approaching 0 lead to collections of rectangles that approximate this region with increasing accuracy, as suggested in figure 5.10. Here the width of the rectangle is greater than the widths of the rectangles in this case, or the number of rectangles in this case is less than the number of rectangles in this case, and you can see the accuracy is increased by increasing the number of rectangles or the number of subintervals. So we'll see in the next section that if the function f is continuous over the closed interval AB, then no matter how we choose the partition P and the point ck in the subintervals, the Riemann sum corresponding to these choices will approach a single limiting value as the subinterval width approach 0. So we just have to make sure that the length of the subinterval is approaching towards 0 in order to make sure make the better approximation of the area under the curve. So that's all for today. Rest we'll discuss in next sections.